Today we're going to look at Chapter 13, Solutions. A solution is a homogeneous mixture which has two components, a solute and a solvent. I want to remind you that a homogeneous mixture means that everything is mixed up evenly and you cannot see little particles inside. It looks all the same throughout. Now, the difference between a solvent and a solute, the solvent is usually what does the dissolving. So, for example, water is a very common solvent, and solutes are what is actually being dissolved. So if we had a solvent at the bottom here of water, and then we had a solute, which could be sugar or salt, and we mix those together and they dissolved, we would have what we call a solution. So although you can't see the solute and the solvent together in the solution, we know that it's in there. Now, when something dissolves, it really is quite an elaborate process. So when we talk about anything dissolving, we're going to use the word crystal because that just means it's some sort of solid. It could be a solid, ionic solid, such as salt or even sugar. And when something is going to be dissolved, you put it into some sort of solvent, such as water. And for example, here in this picture, we have water molecules surrounding a sugar cube. And the water molecules surround themselves in what we call a solvent cage. And each sugar molecule is actually surrounded by water molecules, and that is what actually breaks apart the sugar and dissolves it eventually. Now, ionic compounds are very similar to the dissolving of any sort of solid, but we have to take into account the fact that ionic compounds break apart into a cation and an anion. So, for example, if we had NaCl, okay, which is an ionic compound, it would break apart into the cation, which is the Na+, and the anion, which is Cl-. And you can see here the water molecules orient themselves a little bit different compared when you're looking at comparisons of the cation versus the anion. You can see here that the oxygen molecule is attached to the positive component and the hydrogen is attached to the negative component. Now, if you take another chem course, you're going to learn the term polarity, and that will explain this further. You just have to understand that ionic compounds dissolve in water or any sort of solvent by breaking apart into their cation and anion form. Okay, and that's what helps it dissolve. Now here's a little bit of a bigger picture of an ionic compound dissolving. So here is our ionic compound. Like, let's say we have a big chunk of salt. In this case, it is KCl. So what happens are these water molecules come and they are actually attracted and they pull out a molecule and they create that hydration shell. Okay, and that is what ends up dissolving this, and the amount that can dissolve is basically how many water molecules there are available. So if you run out of water molecules, you don't have any more ability to dissolve any more solid. Okay, so if you have ever put too much salt or sugar into water and it won't dissolve anymore no matter what, that's because you've ran out of water molecules to surround each particle. Now, there are three things that we can do to speed up something dissolving. The most common one is heating up a solution. So when we heat up a solution, we're increasing the kinetic energy, which is the energy of movement, and therefore everything's moving a lot faster, and therefore it can break apart a lot easier because it has so much energy. Okay. Another one is stirring the solution. So if we're adding some sort of movement in, it's getting those molecules to hit each other and collide and break apart faster. Or grinding. So anytime, for example, let's say you have a glass of tea and you have one gigantic sugar cube, or you have like a normal packet of sugar. Think about which one will dissolve faster. The packet, right? So when you grind the solution, you're adding more surface area to whatever you're looking at, and therefore it is able to attack that sugar or whatever on all sides compared to just all sides of just a cube. So whenever you want to dissolve something faster, you can either heat it up, stir it, which sometimes things require both, and make it as small as possible. Okay? Now, this is what we're really focusing on in this chapter, solution concentration. In chemistry, we use the term molarity for solution concentration. You're going to hear that word a lot in this chapter, and we're going to talk about what that means and how to calculate it, but it basically is how much solute, so that's the thing being dissolved, is dissolved in a given amount of solution. Okay, and we're going to be using these terms dilute and concentrated, but when we're trying to look at a specific unit of concentration, we use molarity. So molarity is a big capital M, Okay, not a lowercase m, it's a capital M. And the definition of it is moles of solute over liter of solution. And you're going to see it written like this, and I will provide you with this equation all the time. So moles over liters, so moles of the item dissolving over this total volume of what it's going into. Okay, has to be in liters. So let's go ahead and dive into an example here of how to use this in a calculation. What is the molarity of a solution that contains 24 grams of sodium hydroxide in a 0.1 liter solution? So again, we have this equation provided. Molarity equals moles over liters. And you have to recognize that you currently have liters, which you know you can put it on the bottom, but the problem is you can't take this grams and plug it into the moles. Right? Has to first be in moles before you can do that. So what I like to do is go ahead, and I did show you the work below, but what I like to do is just focus first on converting grams to moles of this compound, which is NaOH. And you have to add up one Na, one oxygen, and one hydrogen to get its molar mass, which ends up being 40. So if you go ahead and divide that, you will get your moles of your NaOH. Erase a couple of things, have a little bit more room here. And then what you're going to do after that is you're going to divide it by liters, which in this case is provided to you. So whatever this answer is, you're going to go ahead and divide it by this 0.100 liters, and this will end up getting your molarity of 6.0. Okay, so I know some people teach it in terms of this dimensional analysis, and if this makes sense to you, that is 100% a perfectly applicable way to do it. I've always been one to kind of break it apart into moles and then solve the molarity equation, but whatever you feel most comfortable with is fine with me as long as you show your units and your work. Now, remember, molarity is moles over liters, and we can use this as a conversion factor, which is what we're going to do in a couple slides here. So it is moles over solution. So if you see a 6 molar solution, you have to keep in mind that that means 6 moles over 1 liter. Okay, so sometimes you can use this moles to liters as a conversion factor to go from one thing to another. So let's go ahead and do another molarity example. How many grams of this potassium dichromate are in 125 milliliters of this solution? Okay, so we're going to go ahead and start with our equation just to know kind of what we're aiming for. We're trying to find grams. To find grams, I first have to find moles before I can go to grams. Okay, so what we're going to go ahead and do is we are going to plug this information in, 0.150 molarity, right there, equals, now we're trying to find moles, and we want to go ahead and plug this in for our bottom component, which is liters, but we have to convert it. So you're going to have to know this conversion factor, which you've had to know all semester long. There are 1,000 milliliters in a liter, okay? And so you're going to actually just move your decimal place over 3 times to the left, okay? So you end up with having 0.150 molarity equals moles over 0.125 liters. So when you have this, I just want to remind you, because I know it's probably been a while sometimes since you've done this, you want to get the bottom number out. So you can go ahead and multiply both sides by that bottom number. So when you do that, it cancels out on the right side, and you're left with 125 times 1.5, okay? When you do that, you go ahead and get, go ahead and continue writing in red here, 0.01875, and I know I'm keeping a couple extra sig figs, but can't be too careful here. Now I'm in moles, and I need to finish off, this question's asking for grams. I'm going to go ahead and do moles to grams, okay? And the big part of this is you need to calculate the molar mass of this, and oftentimes I will give it to you to save you time, but sometimes you'll have to calculate it. So I would look up 2 potassiums, 2 chromiums, and 7 oxygens and add those together, and I would go ahead and get 294.185. Remember, that goes in the gram spot, so I'm going to go ahead and multiply those numbers, and I end up with 5.52 grams of this K2CR2O7. So what does this mean? What does this number even mean in the grand scheme of it? If I went over to the balance and weighed out 5.52 grams of K2CR2O7, and I went ahead and put it into 125 milliliters, my solution concentration would be this 0.150 molarity. Okay? So it actually tells you kind of how to make a solution. Now we're going to go ahead and do another example here, kind of looking at another variable. So we have what volume of 12 molar HCl contains this many grams of HCl. And I actually gave you the molar mass here. And to be honest, I'm going to be writing mm for molar mass, even though the unit does tell you what that is. So I'm going to go ahead and start off with my equation just to kind of give me a goal. And I'm looking for volume, so I'm looking for that. Okay, volume is liters. So I'm going to go ahead and fill this in with 12 molarity equals. Now, the issue with this is I cannot plug a grams into the top because this is where moles goes. Okay, so I'm going to go ahead and come down and do a little side conversion. Grams to moles, because it has to be in moles to be able to fit into this equation. And this molar mass was provided. So to do this math, we can go ahead and do 9.15 divided by 36.46. And we get 0.251 moles. And I can actually go ahead and put that right back up into my equation. And I'm looking for liters. Now this is the hardest for students to solve, so I'm going to go ahead and show you step by step how to solve this. When I want to find a variable on the bottom, I need to get it out of the denominator spot. So since it's being divided by, I'm going to multiply both sides by that variable. Okay, so then let me erase a little so I give myself a little bit more room here. Then my new equation ends up being liters times 12.0 molarity. I came down from here, equals 0.251 moles. Okay, so all I did was get that variable out of the bottom. Then to solve for the variable, I'm going to go ahead and divide both sides by 12.0. This cancels. So the math ends up being 0.251 divided by 12.0. Okay, and my unit answer is 0.0209 liters. Now, if the question asked for this in milliliters, you could do a quick liters to milliliters conversion, and you could say that the answer was 20.9 milliliters. But if it doesn't say and it only says volume, I don't care which one you use. I'd probably use the liters because that's what your answer is provided in. But if you converted it to milliliters, it'd be no problem. Now, we're going to talk about this term dilution, so concentrated and dilution. So whenever we are preparing a solution that we learned how to calculate, we would take a solid, mass it out, put it in water, dissolve it, okay? And then we would call that a diluted solution. But sometimes we need something that is even more dilute than that we can actually accurately measure. So in that case, we would make something more concentrated, okay, and then create a second solution by diluting it. So for example, let me go ahead and show you what we would do. So ignore my artwork. I know it's not great here. So let's say we have a flask, and it is a 2 molar solution of HCl. And then what I need was a 0.1 molar solution of HCl. So my goal is a 0.1 molarity solution. So what I would do is take a certain amount out of this with a pipette, and I'd put it into this other one, fill it all the way up with water, okay, H2O, up to the line, and therefore I could create a weaker solution, a diluted solution. Okay, so this would be the concentrated, and my diluted would be what I was looking for. Now, we have an equation to calculate this. The equation is M1V1, M2, V2. So M is molarity, V is volume, M2 is molarity, V2 is volume. So I'm going to go ahead and go through just some examples of these variables, and then we're going to do a couple practice problems. So M1, I like to say that this side over here is about the concentrated solution, and in my picture up here, it's the one on the left. So this is the concentration of the concentrated solution, SOLN, I'm going to write for solution. So this is in terms of molarity, unit we just used. And V1 is actually the hardest. So we're going to take a little break. We're going to come back to that one, I should say, okay, when it makes a little bit more sense when we understand the other variables. So M2 and V2 are the diluted solutions. So that would be everything regarding this solution on the right here. And M2 is the desired diluted solution molarity. So it's basically like, what do we want to make? And this unit again is molarity as well, big M. And then V2 is my total volume of diluted solution. So for example, in that picture above, maybe this flask was 100 milliliters, for example. So that would be my V2. Now, what I wanted to come back and talk about is V1. V1 is basically how much you would be pulling out of the first concentrated and putting into the second. So it is not the total volume, okay? It is how much you take out of the concentrated solution. Running out of room, so I'm going to just write concentrated solution there, okay? So it's how much you take out. So this is the initial molarity, which is 2 molarity in my picture. V1 is how much you take out of it, okay? So it's not going to be the whole thing. Then M2 is what you want to make, and V2 is what you are intending the whole size to be, okay? So let's go ahead, and you will be provided with this equation as well. So let's go ahead and try an example here. So what volume, looking for a volume of 6 molarity NaOH needs to be diluted to prepare 5 liters of this 0.1 molarity. Now, when I'm doing these problems, if I'm ever having any trouble, I like to actually draw myself a picture to kind of help myself visualize what's going on, and this has helped students in the past. Hopefully you're a better artist than I am here. So what volume of 6 molarity? So the one with the higher concentration, and here's my 2 concentrations, is going to be my concentrated solution. So if I make this one my concentrated and this one my dilute, this is a 6 molarity solution, and I'm trying to make a 0.1 molarity solution. And I want to make 5 liters of this. So this is my total volume, okay? So everything here is my M2 and my V2, and everything here is my M1 and my V1. So what I'm looking for is what volume. So I'm looking for what I'm going to take out to put into this diluted, okay? So I'm looking for V1 here. So I put 6 times V1 equals 0.1 times 5 liters. Now I want to be specific with these units. M's have to be molarity, but V can be either milliliters or liters as long as they're the same thing. So since this is liters, when I solve for V1, the unit would also be liters. If I wanted to make this 5,000 milliliters, that's fine. V1 would end up being in milliliters. No specific units, they just have to be the same for this one, okay? So this tells me that I would pull out 0.083 liters of that concentrated solution, put it into the other one, and fill it up to create my diluted solution. So I have 2 practice problems here. How many liters? So I'm looking for a volume of 0.050 molarity HCl can be made by diluting this, okay? So again, you could go ahead and draw a picture. So I'm going to go ahead and take my 10 molar solution. Again, that equation is M1 times V1 equals M2 times V2. And I'm taking 250 milliliters of it out of it. And I'm trying to make a dilute solution, which is always going to have a lower molarity. And I'm trying to find my V2 here. Okay. So to do this math, I would just take the 250 times the 10, the left side here, and then get that answer and divide both sides by the 0.050. And I would go ahead and get my volume to be 50,000 milliliters. Okay, and how do I know it's milliliters? Because this volume was milliliters, therefore this volume would be milliliters. Okay, so I can make a lot with that. How many milliliters must be taken out of a 6 molar concentrated solution of hydrofluoric acid to make 500 of a 1.5? So I'm asking, how much am I taking out of my concentrated? So therefore, I'm going to be finding V1. So again, this has to be an molarity, and these other have to be just the same unit. So since I'm looking for milliliters, I'm going to leave this in milliliters. So to do that math, I'll do 1.5 times 500, okay? And then I'll go ahead and divide it by 6, and I'll get my V2 to be 125 milliliters. Okay, so I would take, with my 6 molar solution here, I would take 125 milliliters out of it put it into my new one, which is 500, and I would go ahead and fill that up and make a 1.5 molarity solution. Okay. So one of the last concepts we're going to look at in this chapter is solution stoichiometry. So this will bring you back to stoichiometry, which is the mole ratios. Remember when we went from moles of one thing to moles of another, and we used the coefficients in front of the equation. Okay, we call that a mole ratio. That is what we're going to be looking at, but we're going to put it in terms of molarity. Okay, so what mass... Okay, what mass this would be in. So when it's asking for mass, it's asking for grams. Because if I were to tell you to go mass something on a balance, your unit would be grams. Of silver bromide is produced from the reaction of this amount of aluminum bromide. Okay, now when it says an excess silver nitrate, that's just basically telling you this is limiting reactant, and you do not have to pay attention to that. There's no numbers associated with it. Don't worry about it. So it's produced from the reaction of 17.8 milliliters of a 0.105 molarity aluminum bromide. So the first thing I do is just put my information underneath the balanced equation. So you have to have a balanced equation. We do have that provided. So I'm going to go ahead and write down my information underneath the relevant pieces of the equation. So aluminum bromide here, so 17.8 milliliters, and it's a 0.105 molarity solution. And I'm trying to find mass of this. Okay, now to find mass, the only thing I can do in chemistry class is go to moles, basically. So I'm going to go ahead and show you how I start this. I do have the work below, but many different ways to see this written. So first I'm going to go ahead and do a quick molarity equation because I'm provided with what I can change to liters and molarity. So I can go ahead and take 0.105 molarity. And I'm going to actually just quickly change that into liters. If you're at all confused, please go ahead and do the 1,000 milliliter conversion if you're stuck with that. So if I go ahead and solve for that, okay, I would then end up with moles. Let me go ahead and quickly calculate that for you. Give me one moment here. I'm going to take 0.105 and multiply it by 0.0178. Remember, moles are very small, so don't be alarmed and do not cut this off too early. So that's moles. And now the hard part here is units. So first thing we did was find moles. Okay, step one, find moles of what we're starting with. So we started with this aluminum bromide, we found its moles. Now we're going to go ahead and do a mole ratio. That'll get us from this aluminum bromide to what we're trying to finish in. Okay, we just had a test on that, this concept. So this part isn't new. So what I'm leaving goes on the bottom. This should have been a BR3, excuse me here. And then what I'm going to is a GBR. Okay, now I'm going to go ahead and put these numbers in front. There's a 3 in front of that. There's a 1 in front of here. And I'm actually just going to go ahead and solve for this. Okay, and I'll show you what I'm going to do with that next. I'm just taking that number we just got, multiplying it by 3. So I'm going to go ahead and actually write this work down below here. So when I solve for the moles here, I get 0.005607. Now, to be honest, if I had a little bit more room, I would have continued this dimensional analysis, but all I have to do to finish this up is do a moles to grams, and you can see that step actually provided right here. Okay, so they wrote it in one big step, which is great. You can 100% do that. I have found that students have a little bit of trouble doing this first step. You may be fine. That's why I like to kind of do it in the form of using molarity, solving for moles, doing what we've been doing the whole time, mole ratios, and then going ahead to finish off with this grams conversion. Okay, I'm going to show you one more example here. So first thing when I read these types of problems is I first make sure I have a balanced equation, which I do. Second step I do is write everything underneath the piece of relevant information. It helps me keep myself organized. So I'm looking for barium nitrate. So it is 0.280 molarity. And I'm looking for liters. And I'm reacting it with aluminum sulfate. So it is, I'm actually going to convert that quickly to liters. So again, if you're having any trouble with that, please remind yourself how to go from milliliters to liters. Okay, now, how do we know what to start with? You never start with a thing you're trying to find. I'm trying to find this. I'm not going to start with that information. I'm going to start with a thing that has two pieces of information provided. So I'm actually going to go ahead and do a little moles over liter conversion using my molarity. I'm going to go ahead and replace that here with 0.350. Okay, equals, and then I went ahead and solved that in terms of liters. I'm going to solve for that for moles. So step one, as I wrote above, solve for moles. That's always your first step. Okay, so when I went ahead and solved for moles here, I'm going to actually start this down here, 0.00875 moles. Now, I've been teaching this to my high school students recently, and they told me that they were having trouble figuring out what the identity of this was. So that's why I find it handy to kind of do the work below. So we are still in the Al2SO43. Now, step two that I wrote above is do your mole ratio, because if I'm here and I'm trying to end it in another thing in a balanced equation, the only way I can do that is if I go ahead and use a mole ratio. Okay, so what I'm leaving, or what I started with here, goes on the bottom. What I'm trying to end with goes on the top. I'm going to go ahead and use these coefficients, 3 here and a 1 here. Now, this is a little bit different. Our last example, we went directly to grams, so I just did one more step for grams. This one requires another sort of molarity equation here, so I'm actually going to finish this in terms of moles. Okay. Now, moles of what? Moles of the thing on the top, BaNO3, 2. Now we're going to go ahead and do one more molarity equation to finish us off, because now I have moles of BaNO3 and I also have molarity, and I'm trying to find liters. Okay, so I'm going to go ahead and plug our information in here. 0.280 molarity equals 0.02625 moles. Okay, over liters. And I showed you how to solve for something on the bottom prior, so if you need help with that, go back. And when I went ahead and solved this, my answer was 0.09375. I know I went over a couple sig figs there. Liters. Okay, so that means how many liters would I need to react with that? It would be about 93.75 milliliters, or 0.09375 liters. Okay, and let's go ahead and throw our unit on here of barium nitrate, BaNO3. Always good to do a unit whenever we're working with dimensional analysis in terms of solutions. All right, so this is our last chapter in this course. You need to know what the solute is, a solvent, and a solution. Just generally parts of dissolving an ionic compound. I will not have you write every step. How to increase the rates, so stirring, increasing the temperature, things like that. How to do molarity equations. I will provide you with this equation at all times. Also, how to do dilution. I will provide you with M1V1 equals M2V2. And you have to understand how to do solution stoichiometry.